So in this section, I'm going to describe about string compression and Burrows-Wheeler transform. In the previous section, Phillip gave a great description of the suffix tree. It allows us to find a pattern very quickly. But at the same time, the memory and the runtime required for constructing the suffix tree for the genome is linear, big O of the size of the genome. But if some of you believe Phillip and trying to construct a suffix tree for mammalian genomes on your desktop or laptop, you will have problem with memory. Why? Because the big O notations here ignores an important constant. The best known suffix tree implementation requires about 20 times the length of the genome. Can we reduce this constant factor into 1 or even smaller? I now switch the topic. I want to talk about genome compression. It seems to you that Sean just changed the topic very quickly. But I will promise that the thing that I'm going to describe, that is how to compress a genome, will have a relation to the problem that we are discussing today, that is multiple pattern matching. But allow me to describe the genome compression first. Give you this string. Is there a way to present it shorter, or is there a way to compress it? Well, you can see that you have a lot of runs of G and C and A and T and so on. So instead of writing the genome in this form, you can write 10G instead of writing 10G. You just write 10 and G. Instead of writing C 11 times, you can just write 11C. So you see that if the genome has a lot of runs like this, it would be easy to compress. But the problem is that the genomes, they don't have lots of runs. But they do have lots of repeats. Can we somehow transform the genome with lots of repeats into another string, genome star, with a lot of runs, and then run the run length encoding algorithm to compress the genome? How we do with this step? Let me describe the Burrows-Wheeler transform. Let's have a string, banana, bananas, terminated with a special character, $. Let's first form all cyclic rotations of Panama banana. We start with B, the next one is $. Next one start with S, and so on and so forth. We start at the next position. So there are n possible rotations, right? Yes. What should we do next? Now, I sorted all the strings in lexicographic order. You see the color here, just to show you that these strings are sorted. What is the Burrows-Wheeler transform of this text? If you take the last column of this text, it is called the BWT. But why would we care about the last column? Well, let's look at an example. This is actually the text from Crick and Watson for the double helix structure of the DNA. And this is the one region of the BWT. So you see, the last column is BWT. It has a lot of runs. Why? Because the text here has a lot of repetitive words. In this case, it is the word and, A-N-D. You may ask me another question. Why don't I choose the first column as a BWT? Well, it also contains a lot of runs, right? Yes. But I believe Phillip will give you a better explanation.